So in the proof of uniform convergence theorem in week 5, we define 5 different conditions: E1, E2, E1 star, E2 star, and E2 prime. So in this video clip, I will explain the relations between E1, E2, and E1 star, and E2 star, and E2 prime. First of all, the definition of E1 is this: there exists an H such that the test error of the hypothesis class and of the hypothesis and the training error has difference at least epsilon. Okay, so here the key point of E1 is there exists. So when there exists any hypothesis that satisfy this difference between training and test error, then E1 hold. E2 condition is really more restrictive compared to E1. So here, again, there exists an H hypothesis such that the condition of E1, and also the additional condition is defined for S prime, the independent sample set S prime. So the meaning of E2 is there exists hypothesis H such that the first training sample set having at least epsilon difference between training error and test error. And for the second half of training sequence, training samples, we have at most epsilon over 2 difference between training and test error. Since there is one additional condition compared to E1, E2 is more restricted case, so E2 is subset of E1. So when E1 hold, when E2 hold, then E1 also true. And key point of E1 and E2 is there exist. That is difference between E1 and E1 prime and E2 and E2 prime. So E1 star and E2 star defined for a given H star. Okay, for a given single hypothesis, we define E1 star like this: the probability a given the event a given hypothesis having at least epsilon difference between training and test error. And E2 star is defined for the same hypothesis H star, and the condition of E2 star is like a E2 condition. We have difference between training and test error at most epsilon over 2. Okay, so when E2 star is true for given E1 star, okay, when E2 star is true for given E1 star, then which means H star satisfy both condition, and which also means E2 is true for given E1, because E1 condition is there exists an H that satisfy this. E2 condition also there exists a condition, a hypothesis such that this. Okay. Let me give you some image that could be more clear. So basically, E1 condition think there exists any hypothesis. So when there are some hypotheses that satisfy the condition that the difference between training and test error is at least epsilon, E1 is true. And under the given condition E1 is true, when E2 is also true, when among these hypotheses that satisfy this condition, if there exists at least one hypothesis that satisfy training and test error difference is at most epsilon over 2, then E2 given E1 is true. Okay? On the other hand, E1 star and E2 star are defined for one particular hypothesis. We are interested in one particular hypothesis, H star. Okay, and E1 star and E2 star for given E1 star means this is true when this particular hypothesis H star is also true for the E2 star condition. The difference between training and test error is at most epsilon over 2 for the second part of training data point. Under the condition H star satisfy the condition of E1, the difference between training and test error is at least epsilon for the first part of training data point. Okay, so we just considered this particular hypothesis. Under the condition H star satisfy E1 star condition for the first half. So E2 star given E1 star is more restrictive case because in this case we just considered this single particular hypothesis, and we are considering the event E2 star is true when this specific hypothesis is also true. But in this case, E1 can have many different hypotheses that satisfy the condition, the training and test error difference is at least epsilon. And E2 given E1 is true when among these hypotheses, just one single hypothesis is true for E2 case. Okay, so when this particular hypothesis is given to us and this satisfy E1, when we have this condition, what is the probability of E2 is also true? This is more restrictive case compared to considering entire hypothesis that satisfy E1 condition. So this particular case has less probability dense mass. Okay, so from this you can say that probability of E2 given E1 is bigger than probability E2 star given E1 star. And in the proof we show that this is greater than 1 over 2. So from this we know that probability of E2 given E1 is bigger than 1 over 2. E2 prime is a little bit different. Basically in the proof we want to upper bound the probability of E2 so that this is less than or equal to delta over 2. That is our goal of the proof. But the problem is this probability is not easy to analyze. So instead of analyzing probability of E2, we rather consider the probability of E2 prime. And since we are considering upper bound of probability of E2, it is enough to say probability of E2 can be upper bounded by probability of E2 prime, and this is upper bounded by delta over 2. Then we can conclude the probability of E2 is upper bounded by delta over 2. Right? So we define E2 prime as a relaxed version of E2 condition. So basically in the E2 condition, we need two things. The first half of training data point has difference between training and test error at least epsilon. And for the second half of our training data point, we have the difference at most epsilon over 2. So on the E2 condition, the training error for the first half and the training error for the second half, the difference should be n is epsilon over 2. Okay, so E2 prime is kind of superset of E2. Okay, because E2 hold, when E2 hold, this must be true as well. Okay, so E2 prime is a superset of E2. So from this fact, we can upper bound of probability of E2 by probability of E2 prime, and then from the remaining proof, we show this, and then we can conclude this, and we can conclude the theorem.